Everyone, this week's lecture will be on vector spaces and linear independence. So what you could think of as basic linear algebra. So what actually is a vector space? So a vector space is going to be an algebraic object where we have a set V of vectors, so V of vectors, and a field F of scalars. And we're going to endow it with two operations. So the first operation is addition. So I'll say plus V cross V to V. So we take two vectors from V and send them, so like say A and B, and we send them to A plus B. And this has to be associative and commutative. So A plus B equals B plus A, and say A plus B plus C equals A plus B plus C. So associative and commutative. Okay, and in a vector space, we always have a zero element, so there's always a zero such that 0 plus any vector equals any vector plus 0 equals that vector. And we always have an additive inverse, which means for all vectors in V, we have some additive inverse, which we can call negative A, minus A, whatever, such that A plus minus A equals minus A plus A equals that zero element, or the zero vector. All right, and we also have the second operation, which is going to be called scalar multiplication. So you can think of scalars as just like regular numbers. They're distinct from the vectors. So scalar multiplication, we'll denote it by a dot, but just to make sure we can write it out as an operation, we never actually denote it as a dot because the dot represents something else, which is the inner product, which we're not going to be doing, but it's also known as the dot product. You've probably heard it before. And if you have an inner product, you call it an inner product space instead. But just know that this is not the standard notation. I'm just using this so I can write it as an operation. But we have V cross F 2V. So we take a vector. So we'll call A and B and C and F. And we take a scalar and we send it to that vector. So yeah, and this has to satisfy. So let's let C and like C1, C2, these are all going to be scalars, okay? So we must have that C1, C2A, parentheses, sorry, equals C1 times C2A. We must have that C plus B equals CA plus CB, so distributivity, and we must have that C1 plus C2 A equals C1A plus C2A. And that is all you need to know because those are all the vector space axioms. You will see the word axioms in reference to algebraic structures a lot. There are the group axioms, ring axioms, vector space axioms, etc. So now let's look at an example. So we have a vector space in obviously just real numbers. Or no, Rn is a vector space. Okay? Well, I guess let's think of R2. So we have, and the field is going to be R. Okay? So we have vectors, right? Just normal vectors like 2, 1, 0, 1, E, pi, whatever you want. And we have scalars, which are just random real numbers, like 1, -1, e over pi, again, whatever you want. And obviously we have vector addition, like if we sum these first two, we get 2, 2. And obviously you have scalar multiplication, we can multiply this vector by the scalar -1, and we can get -2, -2. Okay? And obviously we have the additive inverse is just the vector multiplied by the scalar -1. The 0 vector is just 0, 0. And I'm not actually going to go through and manually verify all those axioms about like associativity, commutativity, distributivity, because it's not very insightful. It's just the same each time. But another example of a vector space is going to be the set of all polynomials with their coefficients in some field. So let's call that field F. We have F of X. This notation may be familiar. It denotes many things. It can denote the ring of polynomials with coefficients from that field F. It can denote many things, but for our purposes, it will be known as a vector space. Okay? So every F of X, every polynomial in F of X can be written as the sum of some Ck times X to the K. Right, where our Ck are scalars in the field. And obviously the sum of two polynomials evaluated as x is equal to the evaluation of both of the things you're adding. Well, how does this work again? I forget. Whatever. And if you take some d in f, so let's take f to be the real numbers, then like 2.1 times x, right, of say 1, it's going to be 2.1. And similarly, 2.1x of 1 equals 2.1. Hooray. Thinking of polynomials as vectors is actually very helpful for certain things, which we'll see shortly. Anyway, let's talk about linear combinations. So some vector b in our vector space V, in general, V is going to denote our vector space from now on, is called a linear combination if we can write b as a sum of like C1A1 plus C2A2 plus CK, where our AK are vectors and our CK are scalars. So for example, the vector 2, 1 is a linear combination of the vector 1, 0 and the vector 0, 1. Now, that's really all there is to linear combinations. Well, they do have, well, they underlie many things. So now we'll talk about vector subspaces. So a subspace, let's say W is going to be a subset of V, is a subspace if W is also a vector space on the same field using the same operations from its parent set. So it inherits the operations, and it must hold for W as well. So we have a result about these things, is that to show W is a vector subspace of V, all you need to do is show that W is closed under addition and scalar multiplication. Okay, so what we mean by closed is that obviously you don't get an element outside of the subspace. It's like set if you perform the operations from the parent using elements within the subset. So let's look at another example. So let's take the same thing from before, this set of polynomials with coefficients in the field. Let's use the integer. So let's do z of x here. Okay, so what is a subspace? All polynomials p such that the degree of p is less than or equal to 2. So we can check addition. X squared plus x plus, say, minus x squared plus 3x equals 4x. And this also has a degree of less than or equal to 2, so we're good. And we can multiply 4x by 2, and we get 8x. And this is also a polynomial with degree less than or equal to 2. Hooray. What is not a subspace? All p in Px such that degree of p equals 2. Now let's look at the same example above, because these two right here are both technically members of this, like they satisfy this condition, but when you add them, you get 4x, which does not have a degree of 2. So it's not a subspace. And you don't have to verify the other thing, even though it actually works for the other thing, because it fails the first part. Oh, that is not what I wanted to do. Whatever. Now let's talk about span. So let's call S a set of vectors from V. Okay. Let's call WV the intersection of all subspaces of V containing S. Okay. Now if S is a finite set, then we call W as the subspace spanned by the set S. Okay. And if you think about it, if these subspaces have to contain S, then they must contain all linear combinations of the elements of S. And since we're doing the intersection of all subspaces containing the set, the W has to contain only the linear combinations of S, of the vectors in S. Okay. And we can, well, that's kind of a hand-wavy argument. You can formally prove it, but again, it's not that instructive. But yes, so the spanning subspace here is just all linear combinations of the, say, A1, A2, AK in S. Nice. So now let's talk about linear independence, which is our other topic, which comes actually pretty nicely from this. So a subset S of some vector space V, a subset S of some vectors V. is linearly dependent. Not independent, but linearly dependent. Sorry, I don't know why the eraser is broken. Is linearly dependent if for some scalars C n, okay? Right, and we'll say S is the same AK from before. We have that the sum of CK AK equals 0. For some of these vectors AK. So, sorry, what I mean is that for some of these AK in S, but it doesn't necessarily need to be all of them, okay? So, like, we can have, let's say, 1, 0, 2, 0, and 0, 1. This is a linearly dependent set because these two, if you multiply this by -2, you will get 0 if you add them. So, yeah, does not need to be all of those S. Okay, so a set is linearly independent, so linearly independent if it is not linearly dependent. Okay? And the importance of this is what we'll call a basis. A basis is a linearly independent set which spans a space V. Okay, so what this means is that every vector in V can be written as a linear combination of the linearly independent vectors in the basis. So why you want them to be linearly independent is because if you have a linearly dependent set you're calling a basis, it's redundant because you don't need all of those vectors. And the cardinality of this set is going to be important later when we talk about dimension. So let's get an example of so a basis is going to be a linearly independent set which spans a space V. Okay, so what we'll call the standard basis of the real numbers, or not, yeah. So what's the standard basis of Rn? Standard basis is going to be the set 1, 0, column 0, 0, 1, 0, here. Obviously, these are linearly independent. It's impossible to write 0, 1, 0 as a linear combination of this is 1, 0, 1, 0, 0, and 0, 0, 1. And every vector in Rn can be written as a linear combination of these vectors because you can just, if you decompose the vector into its n elements, all you need to do is multiply the basis vector with a 1 in that row by the value, and you get the vector. So this is called the standard basis. So for R2, it's just 1, 0, and 0, 1. Oops. And for R3, these are the two most common things we deal with, by the way. It's 1, 0, 0, 0, 1, 0, and 0, 0, 1. You will see these denoted by I, J, and K sometimes. These three right here, I, J, and K sometimes. When you look at vector algebra, and then multivariable calculus, physics. So a lot of times they write vectors as linear combinations. Like, so you can write 2, 1, 3 as 2i plus 1j plus 3k. You see that sometimes in physics. Uh, okay. And bases don't necessarily have to be finite. So consider, again, this all real polynomials. Okay. So the set of all real polynomials. This has an infinite basis because, well, obviously we have 1, we have x squared, xn for any value of n, and it keeps going because you can have any degree you want as long as it's an integer, and they are infinitely many positive integers. So the basis is infinite. So the basis does not need to be a finite set. So the cardinality of the basis doesn't need to be finite, and this concept of the cardinality of the basis is now going to be relevant. So dimension. So if you think about it, any set of linearly independent vectors can form a basis, because you can always write the vectors in R as linear combinations because these are linearly independent. Now, this is motivated by what we'll call dimension of a subspace. So the dimension of a vector space is the cardinality of its basis. Now, the basis doesn't have to be, you don't have one basis. You can have as many bases as you want. And every basis has the same size. They all have the same cardinality because there is a result where if you let V be spanned, so in the sense it has a basis of some A1, A2, all the way to AN, then you cannot have a linearly independent set with more than n elements. And if you have two bases, and these aren't linearly independent sets, they have to have the same size, which you can prove by a simple, if you have one as m, one as n, then m is greater than or equal to n, while n is greater than or equal to m, so you force them to be equal. Okay. So dimension is the cardinality of the basis. So for like R2 has a dimension of 2. And that's all we're going to cover up to there. So a basic treatment of vector spacing. Now we can do some cool stuff with linear independence. Let's do a Putnam problem. This is going to be Putnam 2003 B1. So the easiest problem from part B. It asks, do there exist polynomials a of x, b of x, c of y, and d of y such that 1 plus xy plus x squared y squared equals ax cy plus bx dy. And this holds identically. So I'll give you like 5 seconds to think about it. All right. So the answer is no. Okay. No. So let's suppose that it holds for the sake of contradiction. So what? Okay, for the sake of contradiction, suppose that it holds. Let's set y equals -1. We'll get the polynomial 1 minus x plus x squared. Okay, if we set y equals 0, we get the polynomial 1. And if we set y equals 1, we get 1 plus x squared. Now, if you notice, in the vector space Rx, these are linearly independent. What does this mean? It means that they cannot be written as linear combinations of two polynomials, right? But also, from the problem statement, if this whole thing holds, then these need to be linear combinations of the polynomials ax and bx, or a of x and b of x, right? So we've reached a contradiction. So it's false, because we can't write these as linear combinations of b of x and a of x for all values of y, right? Because c of y and d of y are going to be scalars then if we're manually setting values of y. So it fails. And there you go. Although obviously, if you want to prove it for arbitrary x, you can do the same thing. You just swap now the a of x and b of x are scalars, and the c of y and d of y are going to be vectors. But this, you get the same thing, so it doesn't actually matter. So we're done. And that's all we're going to be covering today. Sorry for the minor technological issues. I have no clue what's going up with this app, but hope you enjoyed, and see you next time.